Hello class, this is Ms. Friggins with today's video on section 4.6, related rates. As you're watching the video, please remember to write down any important information, formulas, equations, statements, or diagrams, as well as any questions you may have. Feel free to pause, rewind, or even replay the video as often as you need so you can get a better understanding. At the end of watching the video, please write down your summary and your notes and then submit the summary via the online WIS form as well as a top question. Sorry, that's my washing machine going. All right, let's begin. We're going to actually look at a section in the textbook for related rates, but it is in the derivative section, so that's a hint. And the reason why it's a hint is that whenever you see derivatives again are rates of change. And so sometimes the problem may not exactly formally say, find the derivative of this problem. Or use a derivative of this problem, but they will indicate or they will give you information about a rate of change, and then you now as a calculus student can make a connection and say, I may have to use derivatives for that. So there's actually no new content that we're talking about. We're just applying derivatives to a more applied problem. And so an example that's given in your textbook is you have a spherical snowball that's melting. The radius decreases at a constant rate of 2 minutes per second, and 2 centimeters per minute, sorry, from an initial value of 70 centimeters. How fast is the volume decreasing half an hour later? So in my particular case, this is what I like to do for these type of problems. I underline what I'm trying to find because I have a lot of information here, and I'm trying to find how fast the volume is decreasing at a half an hour later. Well, what does that mean mathematically? Well, for me, mathematically, that will be the derivative of the volume with respect to time, where time is going to be half an hour later. Sorry, my horrible handwriting. Okay, now that's what I'm trying to find out, and then I will be able to finish the problem if I know that. So unfortunately, though, they don't give us any formulas because either they expect you to know the formulas or they expect you to be able to come up with the formulas. So the first thing I need to do is figure out of the information they give me, what kind of formulas will I use? Well, I know that we're talking about a spherical snowball, which means it's a sphere. So I know that the volume of a sphere is 4/3 pi r cubed, and you should know that. And so that helps me try to find my derivative of volume with respect to time. But volume is in terms of radii and not time. So I need some function that relates the radius with time. And in this case, it says that the radius decreases at a rate of 2 centimeters per minute from an initial value of 70 meters. Well, that's centimeters, which means now I have my relationship of radius and time by saying the radius is going to be equal to, well, the initial value was 70, and the slope is because it decreases at a constant rate, which means it's going to be a line. The radius function is a line, the slope is -2 centimeters per minute. Okay, and it's important to note that this answer will give me an answer in terms of centimeters as well. And they say per minute, so this is that rate is in terms of centimeters per minute. So why does that help me out? Well, I need to find the derivative of the volume with respect to time at half an hour. Well, since we're dealing with a rate in centimeters per minute, I'm going to change that for t is equal to 30 minutes. Okay? Well, so now what I can do is I can take the derivative of the volume function with respect to time using chain rule, basically, essentially, which is dv dt. I actually didn't want that color. Very special like that. Let me scroll it up a little bit so we have more space. Okay, so dv dt can be found by dv dr, which I can determine, and then I multiply that times dr dt, which I can determine that as well. So now all I need to do is figure out what dv dr is and what dr dt is. Well, dv dr, since this is the volume formula, dv dr is equal to 4 pi r squared. And dr dt is equal to, since we have this, dr dt is equal to -2. Okay, so now all I need to do is multiply these two things together, and when I do, I get a statement for volume, derivative of volume with respect to time, to be -8 pi r squared. Yes. Okay. Well, they want to know, back to the original question, how fast is it decreasing half an hour later? Okay, so I have to figure out what is R at half an hour later. Well, I can go in and figure out R at half an hour later by evaluating R when t is equal to 30. So I get R is equal to 70 minus 2 times 30, which is equal to 10. So this answer is -80 pi. Well, that doesn't look right. Oh, I forgot to square that the r is equal to 10. So actually, -8 pi times 10 squared, which would be 800 pi. -800 pi is my answer. Okay, all right. Because that answer is a number numerically, but what does that mean for my situation? That means that the volume is decreasing at a rate of -800 pi, and we have to put units, which is centimeters, square per minute. Okay, sorry, my handwriting is horrible. And if I plug this into the calculator, it will give me approximately around 2,500 centimeters squared per hour. All right, so that's an example of using rates of change and derivatives to solve a problem. But let's take a look at another problem, and we're going to look at some strategies on how to solve these type of problems. In this case, we have that same spherical snowball, but it's melting in such a way that the radius is, radius is 20 centimeters, its radius is decreasing at a rate of 3 centimeters per minute. So that seems to me like at that particular time, you have an instantaneous rate of change. And the rate at which the volume of the ball, at what rate is the volume of the snowball changing at that instant? Okay, so we're going to solve this problem using these strategies. Will drawing a diagram help me understand this situation? No, not really, because I know what a spherical snowball looks like. But for some of you who may not, that may help. Question 2, what is the data? Well, the data that I have is that we have the radius is 20 centimeters. And the radius is decreasing at a rate of 3 centimeters per minute. So I'm going to say dr dt is equal to -3 centimeters per minute. I have that's a spherical snowball, which means that when I talk about, the question is asking about what rate is the volume of the snowball changing at that incident. In this case, that's dv dt when the radius is equal to 20 centimeters. Oh, I'm writing horribly. Okay. So then in this case, what information do I have from the statement of the problem is I know that it's a sphere, so that means my volume is going to be a formula based off of that color, 4/3 pi r cubed. Okay, so the unknown is dv dt when the radius is, oh my gosh, that's so horrible handwriting. Move that right here. Okay, sorry, I have to fix that. Okay, when the radius is 20 centimeters. Okay, so what notation would help? What introduce suitable notation? That's fine. I think you can take it from here. So to do that, so I kind of did question 4 kind of in here already, because that's just something that I do naturally. The notation is dv dt. We do have a dr dt as well. So now the step 5 is how can you write the data with the known information using the notation you introduced? Well, more or less, I believe you can do all this stuff without that. So let's go ahead and start solving the problem. We're trying to find dv dt when the radius is equal to 20 centimeters. Unfortunately, like the previous problem, we don't know what's going on with the radius at other times. We only know what the radius, what's going on with the radius when the radius is equal to 20 centimeters. So I'm going to take the derivative of this function. Okay, this video is a little bit longer than I planned, sorry. So I know that the derivative of volume with respect to time can be done using the chain rule, which is 4 pi r squared times dr dt. Okay, well, I notice that my radius is 20 centimeters and that dr dt at that point is -3 centimeters. So all I have to do is substitute here, which is 4 pi times 20 squared. Like last time I forgot the square. Times dr dt, which we know is -3 centimeters per minute. Okay, and then as a result, we get our answer to be approximately, let me scroll down so we can see. This is 400, this is times 4, so this is approximately, well, exactly 1600 pi times -3, sorry. 5800 pi. And then the units, since it's the rate of time, this was centimeters squared times the centimeters, so it's going to be centimeters per minute. Okay. Okay, I made a numerical error. 3 times 16 is not 58. It is 48. And then it's centimeters squared times centimeters, so this should be centimeters cubed. And this is my answer. And I just go back and check to see that I solved the question. I'm trying to find dv dt when the radius is 20 centimeters. Well, the dv dt is exactly 4,800 pi centimeters cubed. All right, that's it. Sorry the video is a little bit long because of my mistakes, but I hope you enjoyed it. If you don't like me doing all these examples, feel free to let me know. And that's it. All right, bye-bye.